Welcome to Lecture 1.2, Plotting Solutions to Differential Equations. In the previous lecture, we saw what differential equations are, and we saw how they can model real-world situations. We still haven't seen how to solve them, but in this lecture, before we see how to solve them, we are actually going to see how to visualize the solutions and how to plot them, again, before we even know how to solve these things. Let's start with an example. Before I do the example, I'm going to point out this terminology. ODE stands for ordinary differential equation. And the word ordinary means that our functions are of one variable. A much more advanced topic, and we'll see a little bit of this at the end of the course, are differential equations where the functions are of two variables. For example, maybe of time t and of space x. These are called partial differential equations because they involve partial derivatives, and we call them PDEs. So there's ODEs and PDEs. Some people call ODEs diffEQs. Depends on what part of the country you're from. It's definitely a regional thing. But okay, let's continue this example. So consider an ODE involving a function y, and consider this equation right here. So we don't know how to solve this equation yet, but in this lecture, we're going to see how we can visualize the family of solutions. Now remember, there's not going to be just one solution to this. There's going to be a whole infinite family because there's going to be a constant of integration that's going to appear. Okay, so before I show you the real method, that's the topic of this chapter, I'm going to show you sort of a dumb way to do this. This is a naive way that's not going to work very well. So let's plot. So we want to plot the solutions. So functions y of t. So this, so what we're going to do in this sort of dumb example is I'm going to mark off integer lattice points like this, and at each point there's going to be a solution that goes through that point, and I want to figure out what the slope of that solution is. So y prime, so here's our equation. So at the point 0, 0, at the origin, the slope y prime is equal to 2y plus t. So at 0, 0, that's 2 times 0 plus 0 is 0. So that's y prime equals 0. So at the origin, I'm going to draw a little tick mark, a hash mark of slope 0. So at the point 0, 1, y prime equals, again, it's going to be 2 times the y value, which is 2 times 1, plus the t value, 0, and that's going to be 2. So at 0, 1, I'm going to draw a line that has slope 2. Let's do a few more of these. At 1, 0, y prime equals 2y plus t, so that's 2 times 0 plus 1, which is 1. So at the point 1, 0, which is right here, I'm going to draw a tick mark of slope 1. Let's do one more of these. So at 1, 1, y prime is 2 times y, 2 times 1, plus t, and that's equal to 3. So at the point 1, 1, I'm going to draw a tick mark of slope 3. Now you can see this is not helping very much. Ideally, we would like to draw a tick mark like this at every point in the plane, but this is really slow, and I guess we could do it with a computer, but it's not an optimal. It's not an optimal method. Okay, so here's a better method. Let's consider the same differential equation, or same ODE, y prime equals 2y plus t. And I'm going to say that an isocline is a line or a curve in the plane on which y prime is constant. So let's understand this by example. So let me ask a question. Question is, when or maybe where, is y prime equal to 0? Let's find all the points where y prime is equal to 0 on here. So how do we do this? Well, let's take y prime and plug in 0 and solve for the remainder of the equation. So let's see. So the answer here is, when should be 2y plus t equals 0. In other words, y equals negative 1/2 t. Okay, so let me draw the ty, or I guess the ty plane. That this is t, and that this is y. So this line, y equals negative 1/2 t, goes through the origin and it has slope negative 1/2. And this is where y prime equals 0. Y prime equals 0. So at everywhere on this line, the derivative is going to be 0. So I'm going to, on this line, draw these horizontal tick marks or hash marks that have slope 0. Okay, let's keep going. So here's my next question is going to be, maybe I should say where. Well, I guess t is time, so either one. When is y prime equal to 1? So the answer, just go back up to here and plug 1 in for that. And if you do that, you get 2y plus t equals 1. And that's just y equals negative 1/2 t plus 1/2. So that's a parallel line, but it intersects at slope 1/2. So let's draw that here. So along this line, this slope is going to be 1. So this is, I'm just going to put equals 1 right there. So y prime equals. And then we can continue. So I'm going to, continuing, we say y prime equals 2. I'll let you do the fill in the math, but it's not hard. That happens when y equals negative 1/2 t plus 1. Y prime equals 3. That happens when y equals negative 1/2 t plus 3/2. So let's fill in these lines. These are going to be parallel. And this is when the slope is 2. This is when the slope is 3. So I'm going to draw tick marks that are steeper and steeper still. And let me do one more. Well, actually, let me do several more. Let's see. So y prime equals about a negative 1. That's going to happen when y equals negative, it's supposed to be an equal, sorry about that, y equals negative 1/2 minus 1/2. So that's going to be down here. On here, y prime equals negative 1. So now that's going to be slightly steeper than the slope of this line. And it's not hard to see that if you can see the pattern. The slope's going to be negative 2 along this line. But I want to point out one more interesting case. So let's notice that y prime equals negative 1/2. That's going to happen when y equals negative 1/2 t minus 1/4. In other words, along this line here, the slope is going to be exactly negative 1/2, which is exactly the slope of this line. So in other words, this line is actually going to be a solution. Okay, so what I want you to think about this picture, here's how I want you to think about this picture. Think about this picture. This is called a slope field. I should probably say that. This is a, where should I write that? How about this? I need a pen first. This is a slope field. And think about this like a bunch of currents in a lake or a river. So let's suppose I ask you, sketch up here, I'm going to say, sketch the solution to this differential equation that satisfies y of 0 equals 1. So find the solution that satisfies that at time equals 0, y is 1. So again, this is the t value, this is the y value. So what we do is we go to the point 0, 1 on our here, which let's see where that is. So that's actually right. Which one is that? That's right here. Is that correct? Oh no, that's not. Yes, that's right here. So we go right here. This is the point 0, 1, and then we pretend that these lines that we've drawn are like the current in a lake or a river, and we imagine what curve goes through this point. So we sort of filled in like that, and this is the particular solution, y of t, that satisfies this equation and goes through that point. Okay, let's do a different one. Let's suppose instead I had asked you, which one do I want to do now? What if I said y of 2 equals 1? Well, then we go over to the point 2, 1. So we go, that's 1, there's 2, and we go up. Here's the point 2, 1. And we fill in what curve goes through that point. Similarly, you can tell that there's going to be a curve that looks like this. There's going to be a curve that looks like this. So these are things that I'm drawing. This is the infinite family of solutions to this equation. Now finally, let me ask you one more. So this is, let me call this part 1. Let me call this, cross that out, let me call this part 2. Suppose I had asked, so here's part 3. Sketch the solution that satisfies y of 0 equals, how about negative 1/4? So that's the solution that goes through here. So what if this is like a little twig in this river with, these are the currents, and the twig is right there. What's the trajectory of that? It's going to lie in this line forever. So this line, which is this function right here, is going to be one solution to this equation. And in fact, it's the easiest, the simplest solution. It's the only one that's a straight line. Everything else is some sort of curve, and we'll understand later what the nature of these functions are. Okay, so here's another example. Let's sketch the solutions to this equation. Let me rewrite this as y prime equals y squared, and I gotta be careful because this is a prime, not a 1. That's a 2. So let's do the same thing we did before. Let's say, well, when y prime is 0, so let's take y prime and let's plug in various values for it and solve for y. So when y prime is 0, then clearly y has to be equal to 0. When y prime equals 1, then y squared is 1, so we get that y equals plus or minus 1. When y prime equals 4, plugging in 4 over here, we see that y squared equals 4, so we get that y equals plus or minus 2. And you can see the pattern here. When y equals 9, or when y prime equals 9, then y equals plus or minus 3. And if y prime is negative 1, there's no solution. Okay, so let's draw this. Let's draw the ty plane as we did before. This is t, this is y. So when y equals 0, that's this line right here, our solutions have slope 0. So we draw these horizontal tick marks along there. Now when y prime equals 1, that happens along these curves, and y equals 1 that's just a horizontal line. So along right here and right here, we have, our solutions have slope 1. Now at 2, 3, 4. So this is, so at y, actually I didn't need to draw all those lines, but so when y is plus or minus 2, the slope is 4. So along here the slope is 4. That's very steep. And along here the slope is 4. So this is y prime equals 1, y prime equals 4, and then you see the pattern, y prime is going to be 9 along here, so that's going to be practically straight lines. I mean, it's hard to draw a little mark like this with much accuracy that has slope 9, but you get the idea. Now your solution curves, there's going to be one that goes right through. The 0 function is a solution, and you can check, indeed, the 0 function satisfies this. The derivative of 0 is 0 squared. Yes, that is correct. And then the other functions, let's just fill in, let's pretend that this is like the currents in a river. And then they are going to go, the solutions are going to go like this. So this is the slope field, and I have drawn some example solution curves on here. Okay, so I will finish this lecture with a shortcut that works for a certain class of differential equations. It doesn't always work, but it works for these. Equations that are autonomous. So an ODE is autonomous if the function y prime can be written as some expression in y. And the key here is that there's no t on the right-hand side. So this is best seen by an example. So let's see. Yes, the following are autonomous. Y prime equals 3y. That's an autonomous ODE. That's something that we saw in the last lecture. Y prime equals 2y minus 3. Y prime equals y squared. That's what we saw in the last slide. Y prime equals y times sine of y minus 1. That's autonomous because there's no t in these equations. Non-examples. So y prime equals 3t. That is not, well, that's not an autonomous differential equation. And now that's actually one you know how to solve. This is something that you can solve with just basic calculus, just integrate both sides. But most of the equations we're seeing, something like this, our calculus isn't going to work. We need more methods. We need new tools. Okay, y prime equals 2t plus y. I think that's the one that we did earlier this lecture. That is not autonomous. Y prime equals 2y minus 3t. Again, there's a t involved. It's not autonomous. Y prime equals t times sine of y minus 1. Not autonomous. Okay, so let's see why this is a special case and why we have a shortcut for this method. And I'll do this with an example. Sketch the slope field of this autonomous ODE. And what I will do is, as motivation, I'm going to recall a problem from basic calculus. So motivation from calculus. Suppose we have not a function, but suppose we have the derivative of a function, y prime of t, and it's t plus 1 times t minus 2 times t minus 4. So notice the similarity between this equation and that equation. So in the first month of calculus, you learn all about derivatives, and then the question is, what is this useful for? And then we say, suppose we have a function like this, y prime of t is this expression. Now at this point, we have not learned how to solve this. I mean, you know how to do it in integral calculus, but suppose you don't know that. So in your first month of calculus, what you do is you plot you say, well, we can't actually solve for y, but we know how to graph y. Okay, and how do we do that? Well, we look for the critical points. And there are 3 critical points in this equation. There's t equals negative 1. And the critical points are the roots of these 3 things. And that's when the derivative is 0. So one critical point is at negative 1. One critical point is at 2. Another critical point is at 4. And we say, that's a 2 and that's a 4. So we say that, we look at these regions and we say that the derivative does not change sign, S-I-G-N, within the regions. It flips signs along these critical points. And at these critical points, we either have a local min or a local maximum, or I guess, or an inflection point. So looking at this, it's not hard to see. Let's take some value of t that's bigger than 4, like t equals 5, and plug that into here, and we get a positive, positive, positive. Remember this? We get plus, 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 and so we conclude that y prime is positive in this region. Similarly, if we plug in a value t equals 3, say, into here, then this is positive, that's positive, and that is negative. So in that case, we get plus, plus, negative. And so we say in this region, y prime is negative. Remember this? You probably do. Similarly, we get y prime is positive here, and then we get y prime is negative here. So then we say we don't know what the function looks like, but we can approximate it. We know that it has a negative slope here, it has a critical point there, then it does something like this, and then it does something like that. And we know that this is our function, y of t, because it has critical points there, there, and, well, I'm sorry for my drawing, right there. Okay, so let's turn our attention back to this differential equation, and now what we're trying to plot is we're trying to plot the solution. So we want to plot, this is going to be t, and this is going to be y of t. So notice, let me ask the question first, what are the steady state solutions to this equation? Are there any constant functions that are solutions? Well, if there are, if there is a y of t that's constant, that's c for constant, then y prime equals 0. So we can look at this equation and let's plug in 0 here, and can we solve for y? And we see yes. If this is equal to 0, then y can be negative 1, 2, or 4. And so y equals negative 1, 2, or 4. So we know that at negative 1, we have a solution. This is negative 1. At 2, we have a solution. And at 4, so all three of these, y equals negative 1, y equals 2, y equals 4, all of these are actually solutions to this differential equation. And now we can do a similar thing. We can say, well, what happens if y prime, or if y is greater than 2? What if at time equals 0, suppose we start at 5 or 6? Then we don't know what the function is, but we know that the derivative y prime is y plus 5 plus 1, 5 minus 2, and 5 minus 4, which is a positive number. So in other words, we know that up in this range, y prime is positive. Similarly, we know in this range, y prime is negative. Again, if plug in, all this is saying is that the derivative is equal to the value of the value is just the height, the value of the function. Well, y plus 1, y minus 2, y minus 4. So if our y value is, say, 3, then in this region we have, if y is 3, then we have positive, positive, negative. So the slope is negative. Similarly, our slope in this region, y prime is positive, and our slope in this region is negative. Let me put a little line here. Okay, so we have, so in this range, our slopes are positive, so our solution curves are going to look, well, they go up like this. It's not clear that they're exponential like this necessarily, but again, we don't need too much accuracy, just like down here, we just need a qualitative picture. Now, in here, in this region, our solutions are positive. And notice that two solutions can never actually cross. With any solution here, it's going to be positive, and it's never going to be 0. It's never going to cross, never going to intersect this line, and it's never going to cross. And if you're not convinced on that, I encourage you to pause the video and take a minute to convince yourself why two solutions can never cross in the ty plane. Okay, so we have solutions, and they really have to, all that can happen is something like this. They have to approach both of the steady state solutions from below and above at the same time. So they have to look sort of like that. Now down here, the slope is negative, so we have solutions that look like this. And again, there's not much choice for what we can have. The slope is negative everywhere, and it has to approach this from above and this from below. And finally, down here, our slope is negative, so that means that our solutions are going to look like that. So we do not know, summarize, in calculus, we do not know, in the first month anyways, how to solve for y, but we know enough to sketch what y approximately looks like. In differential equations, we don't know enough now to solve for y, for this differential equation, but we know how to sketch the family of all solutions. And that's this thing right here.